Welcome to the video tutorial for 9.4. We're going to look at the topic of resolution today. So resolution has a lot to do with things like our eyes, cameras, anything with um, focusing on a light source. So we've got quite a few learning objectives today, but a lot of them are sort of meshed in with each other. So let's begin. Okay, the simplest learning objective is to quote Riley's criteria. So Riley's criterion states that two sources can resolve if the principal maximum of one source is no closer than the first minimum of the other. That sounds like a bunch of words, and right now it probably is. We'll go back and revisit that in just a moment, but um, yeah, we'll revisit that after we look at some examples. So second learning objective is to describe the situation that gives rise to the Riley's criteria. So we're sort of combining both of these learning objectives together because you might say, what is the Riley's criteria? Well, we've got the definition for it, but then you don't really understand it. So then let's look at that situation, okay? Okay, so for now, consider that there are two people, maybe dressed in similar clothing. So maybe they're all wearing black, I guess. And so sunlight is shining on these guys. Maybe not wearing, let's say they're all wearing red. Okay, so let's say they're all wearing red, the same shade of red that is. Okay, so there are two big blobs of red. And so red light, well, white light is coming from the sun. And you, as an observer, are watching these two guys who are dressed in red. And so you can see them pretty clearly if they're far enough apart. Now, as they move closer together, so as Kelly moves closer to Jasper, right, so they're moving inward towards each other, then it becomes more and more difficult to see them. So the idea here is that when they get close enough, they're going to appear as if they were one person. And so Riley's criteria is really about that. Okay, it's about when objects, two similar colored objects, or exactly the same colored objects, can be distinguished from each other when they get close enough to each other. Now, if we think back about our single slit diffraction, we're going to be talking about this a little bit more because when an object, when we get some light onto an object, we're going to see this particular type of interference pattern in the back of our eyes and also in the camera as well, right? Because essentially our eyes and our camera, they refocus light through a very narrow slit. And so the whole idea of the eye and the camera is highly related to this whole single slit idea here. Okay, so you may still not fully understand what exactly Riley's criteria is, okay? We have this rough overall understanding. It has something to do with when things get really, really close together. And then we also know that it has to do something with the diffraction pattern, a single slit diffraction pattern. Now, we are going to get into the details of that now. So we've kind of got this like real world understanding now. And now we're going to be looking deep into the physics of that. So in order to illustrate this, we're going to look at two different patterns side by side and to illustrate cases where the two sources can be resolved, cannot be resolved, or are just resolved in the critical case. So really, I mean, it could be argued, but in terms of what's happening down here, actually, hold on, I'll do it like this is. So first one, this could be resolved. Sorry, I was meant to use the letters. So this can be resolved. This is the critical case C, and this is where it cannot be resolved. So let's understand what this is really talking about. Okay, so I'm actually going to pull Riley's criteria down here one more time. And now we can probably really begin to understand what Riley's criteria is talking about when we look at this example. So I'm going to copy and paste that. Okay, so it's through studying the idea that there's two objects moving close to each other. Now, I purposely use different colors just so that they're easier to tell apart, but we're probably looking at objects that are of similar color. They don't have to be, but it's even more blurry when they are of similar colors. So a few things to note here is that you might notice that I drew a middle line at the center of the diffraction pattern. So there's two gray lines that are the middle of that pattern, okay, or the central maxima, they like to call it. Central maxima. Okay, so the absolute center of that maxima. Right, so central maxima, we've got that identified now. Oops, I went a little bit too far. Central maxima, okay. So what's going to happen is that just like what we saw in our diagram up here, these guys are moving closer together. So that's also going to cause the diffraction pattern we see in our eyes move closer and closer together. Okay, so they're moving closer together. And actually, I'm just going to draw a few reference points here. Okay, so let's say that's a center. Right, so they're moving closer together. Right, let's say they move around there or so. This guy moves about there, okay? And so as they move closer and closer together, they're going to start to blend in with each other, right? Now, where the limit of the resolution, where the critical cases, so beyond this point, they cannot see each other, is exactly stated in Rayleigh's criteria. Oops. So let's do that. Okay, that right there is the critical case. Okay, so how we can tell that is the central maximas really help. So if we look one more time at Rayleigh's criteria, it states that two sources can resolve if the principal maxima, okay, so actually let me just maybe use a different color. I'm going to use purple. If the principal maxima, so that's this purple line right here. Okay, if the principal maxima of one source is no closer than the first minimum of the other. So the first minimum, I'm just going to pull this away back for a moment. The first minimal is right here and here. And likewise, it's also there and there as well. Okay, and so when all of this moves close enough where the central maxima touches the, sorry, that was meant to be over, that's pretty close already. So when the central maxima is over the first minimum, Rayleigh's criteria says that can resolve. And when it moves just beyond that point, meaning if it goes past that, so about there or so. So now it's past that. Now they're blended in together. Okay. So again, if you look back over here at this diagram, that's also what it's trying to illustrate. This line right here, right, is just touching the minima right there. Okay. Likewise, this other central maxima is also just touching the minima from this particular slope right there. All right. So that's Rayleigh's criteria. So now you might hopefully you fully understood what Rayleigh's criteria is about now. So the last part of this lesson, so all three of those learning objectives was to understand the different ways in which Rayleigh's criteria can be put together. Now we're going to look at some simple calculations, which is arguably probably easier. So Rayleigh's formula to introduce is this one right here. That's learning objective number 5. Theta equals 1.22 lambda over b. For this value 1.22, it's beyond the scope of this course to understand that. You could just treat it like Planck's constant or the K constant for the Coulomb's constant. Okay, so just treat it as a constant. It's a number there, like pi, in this formula. All right. Otherwise, we get into way too difficult of physics for this course. Okay, so that's the formula. And then we need to learn to calculate the angle given the distance apart of two sources and their distance of the observer. So we're going to be mastering this or a few variations of this over our next two examples right here. Okay, so just to illustrate, so we might have two objects right here. This is where the observer is. Okay, so the observer is there, the aperture. And so big D, very similar to Young's double slit, is that it's the longest distance between the objects and the observer. And then there is an additional distance here that can be calculated. We'll talk about this a little bit later, okay? And naturally, wavelength of the light is lambda. Okay, whoops, went a little bit too fast. So monochromatic light of 550 nanometers is reflected off two identical surfaces at equal distance to an observer. So I've got a little diagram down there already. If the aperture of the human eye is 5 millimeters, what is the minimum angle that will allow resolution of these surfaces? So what we're given here is we've got the wavelength. I'm just going to switch back to black. It's 550 nanometers. And I'm just going to write that as 550 times 10 to the power of negative 9. And B is the distance of the single slit diffraction, or in this case, it's the aperture size. Sorry. So 5.0 millimeters, and that's, I'm just going to rewrite that as 10 to the power of negative 3. And we're trying to solve for the angle theta. So it's pretty straightforward. I'm just going to copy and paste the formula. Right. And so let's make our substitution. So it's already done for us. We need to solve theta. So 1.22 lambda 550 times 10 to the negative 9. 5 times 10 to the negative 3. Excuse me. Let me just pull my calculator right here. 550 times 10 to the negative 9 divided by 5 times 10 to the negative 3 and multiply that by 1.22. So we get about 1.342, but our smallest value is two significant figures, so we'll just round that off to 1.3. So angle is 1.3 degrees. Actually, no, that's not in degrees, that's in radians. Okay, so sorry, I forgot to mention that. This is, the angle is measured in radians for this particular formula. So make sure you guys make a note in your formula booklet for that. A lot of things in chapter 9 tend to be in radians, but every once in a while they throw in a measurement in degree, and it kind of throws everything off. Okay, our next example is we got a satellite orbiting at 400 kilometers above the surface of the Earth. There's two light sources attached to the satellite, 22 meters apart. Each light is 600 nanometers. On Earth, the telescope has an aperture of 70 millimeters. So this time, we're asked what is that minimum angle that the light source can be resolved. So if they're far enough, no problem. What happens when they move too close? Okay, let's maybe just, I'm going to redraw this diagram in a slightly more simplified format. So we're trying to figure out that minimum angle. We know the aperture size is 70 millimeters here already. And we know the wavelength is 600 nanometers. And now we are being asked to solve for the, can this telescope resolve this or not, okay? So does this satisfy Rayleigh's criteria? this is where it's kind of interesting. Um, so we have D. Is D? Yeah. No. B is the aperture size. B is the aperture size, which is what is that? 22 millimeters. The big distance D is 22 meters, and wavelength is 600 nanometers. And we're asked to solve for angle theta. Okay, so we can apply Riley's formula one more time, but we don't know what the actual angle is. So, or sorry, what the minimum angle is going to be here. Okay, so let's, why did I not copy properly? Okay, I'm just gonna go up and grab this one. Copy and paste. Okay, so we've got the wavelength of light, which is, I'm gonna write that first. Wavelength is 600 millimeters. And B, the aperture size, is 70 millimeters. So that's pretty convenient. Oh no, that's nanometers, isn't it? That's nanometers. Okay, so so once again, 1.22 600 times 10 to the negative 9. This is 70 times 10 to the negative 3. Okay, and we make our calculation here. So 1.22 times 600 times 10 to the negative 9 divided by 0.007. So we're looking at 1.04 times 10 to the negative 4. This is in radians. And so can the telescope resolve this or not? Now, there's a little bit more of an interesting piece of information because we found the minimal angle according to Riley's formula, but this actually has an angle of its own given the trigonometry that's already here. So let me just maybe illustrate this one more time. So this actually has a set angle, which we have to compare it with Riley's criteria. So this is sort of a two-part answer. So this minimal angle, we've already calculated about, but what is the actual angle? Because we know that this has a distance d, and that is, was it 400 kilometers? And this distance between the two light sources is 22 meters. So the size of the satellite is about 22 meters apart. Okay, so we've got our two light sources right there, like that. Now, we can use some simple trigonometry to figure this out of what that angle would be. So I'm going to show you two different ways. I'm going to use the long way first. So I'm just going to grab a part of this triangle. That's going to be half of the whole angle. Okay, so we're just cutting that triangle in half like this, right? So I'm just trying to solve for half of that triangle. So now we got a right angle triangle. Right angle triangle. This distance is still 400 kilometers. And oh no, sorry, not that distance. It's the hypotenuse. 400 kilometers. Right, they're both 400 kilometers. That's the 400, not the middle line. And this is half of 22, which is 11 meters, right? So we're taking this half of that triangle, and we're solving for that. Okay, so this is sine, right? Sine is opposite SOHCAHTOA, sine of the angle. So that means we have to double the actual angle afterwards, okay? So we're just going to treat this as simple trig first. Let's solve for this angle, and then we'll double it, which will give us the full equal isosceles triangle. Opposite is 11 meters over 400 kilometers. So let's do this then. 11 over 400 kilometers, and then sine inverse that. And we're going to have 1.5. Angle is 1.57, 1.58. Now this is actually in degrees, times 10 to the negative 3. We're using trigonometry. This is now in degrees. So we need to double this angle. So multiply that by 2. So the angle is 3.15 times 10 to the negative 3 degrees. And so we need to convert this into radians. So we know that, let's see here, how do we do this? We know 180 degrees is worth pi radians, so 3.14 radians. So in order to get a single degree, so in order to get the value in radians, we're just going to build a ratio here, 3.15 times 10 to the negative 3, which means we're doing pi. Where's pi on my calculator? Okay, pi divided by 180 times 0.00315. Okay, and so that's going to give us about 5.5 times 10 to the negative 5 radians. So that's the final answer. Let's compare that with what's on top. Actually, I'll bring what's on top down here. Okay, so this is the minimum angle. And our value is smaller than that, which means it does not resolve because the angle is too small. Okay, all right, guys. So those are, this is a little bit more of a complex question, but that's probably as difficult as you're going to see in terms of Riley's criteria question. Thank you guys for listening. We will see you guys tomorrow on Friday, right? For another physics lesson. See you guys then. Bye-bye. This is a follow-up video, and it looks like I was checking the answers and I made a calculation mistake right there. So when I put 70 millimeters, I think I got lazy and I went 0.007. I forgot that there was an extra 70 there. So that actually turns out to be 0.07 or 7 centimeters. And anyways, so it turns out then that that shifts this decimal by 1. So 1.04 times 10 to the negative 5. And so if we have that then, 1.04 times 10 to the negative 5, this now ends up being a smaller value. So 1.04 is less than 5.5. Oh my God, I can't write. Okay, 5.5, right, because the powers are essentially the same, right? 10 to the negative 5, just cross that off, okay? So now the answer is actually changed, meaning that the angle can be resolved because this is now larger than the minimum or the critical angle, whereas before it was the opposite. All right, guys, quick little fix up. Thanks for watching. See you guys later. Bye-bye.